This is lecture number 5. We have the laws of motion. So up till now we've gotten our units. We've talked about one-dimensional motion. We learned vectors. That enabled us to do two-directional motion. And now we need to introduce some laws that will govern that motion. Okay, so without further ado, we'll go ahead. We'll just get started. So this is all about forces, okay? And forces, they have a pretty easy definition. They're a challenging part for a lot of students because there's just a few of them to learn, and they all have a little bit of a different property, but the general consensus is the same. They're all either a push or a pull. Okay, that's all that happens here. It's either going to be a push or a pull on an object. It is good to note that it does take two objects to create a force. You need something to push or pull against. Many of these things are seen, every day. You push open a door to get through a building. You're, even anything like lifting up a coffee mug or something like that. You're applying a force to it in order to get it to move, in order to cause that motion. All right, so every push or pull can be classified as force. Now, some forces can be directly applied, whereas others are invisible. So, like you might have, opening a door or pulling on a spring or turning a handle. It's a direct application. You're physically pushing or pulling on the object. Kicking a ball, pulling a cart, any of these, right? Anything that involves a physical interaction. Even getting hit in the face by your cat for no reason whatsoever. That's a physical force that your cat has decided to bestow upon you. There are other ones that are invisible. They're not seen. They're still there. They're being applied, but they're a little bit harder to detect. This can be like electric charges, like a positive and negative charge has a force of attraction. Okay, it still takes two objects, still takes two charges, but they'll be attracted towards each other. Same thing with magnets, right? If you have magnets of opposite polarity, like a north and a south, those will be attracted towards each other. They also have, a repulsion, a push away from each other. If you put north on north or south on south, they'll be pushed away. So these ones, sometimes you see them in your life if you have magnets, fridge magnets or whatever. But the big one's gravity. Gravity you can't see, but yet it pulls you down, keeps you on the earth, and it does take two objects. It takes you and the planet in order for gravity to work, and that's what keeps you down and keeps you pulled towards it. Now, we'll talk a little more on gravity towards the end of the semester. And gravity works on any two objects. So there's a gravitational pull between, wherever you are and the next person, next closest person to you. There's a gravitational pull there. If you're in a large lecture center or something like that, you're gravitationally attracted to every other person that's in there and every other piece of equipment that's in there. Basically anything with a mass you are attracted to by means of gravity. Okay? So that's the two types of forces. They are just pushes or pulls in some direction. Okay, it takes two objects. Some you can see, some you can't see. Okay. The mastermind behind forces is, of course, Sir Isaac Newton. Newton was a brilliant physicist. He's world-renowned. He's still known as one of the greatest physicists of all time. He solved so many problems. He was in 1642 to 1727 was his lifespan. He formulated all these basic concepts and laws for classical mechanics. He discovered the universal gravitational equations. In order to get more definite results, as we've seen in this class, to get like instantaneous results, he stumbled into calculus. He invented or came up with the governing laws of calculus and how that those mathematical properties can help us further understand. So, I mean, he developed calculus when he was very young. There's also big discussions on the motion of planets, how the Earth and the Moon and all the planets circled around in these big orbits. He was able to mathematically predict and prove and why the planets did that. And I mean, it was years ahead of his time. People had tried on this for a very long time, and he was able to go ahead and do it. So anyway, very big contributor to physics and a ton of other sciences, to be frank. So you'll see his name pop up all over the place, and it's actually his name that denotes the unit of a force. We call them newtons. So for this class, we're not going to expand into a whole bunch of stuff here, but we are going to talk about Newton's laws. He has 3 main laws for forces, some of which you probably have heard before, or maybe you've heard them in a different way, but we'll go through those. So for Newton's law, you need to know where you stand. Literally, you need to know where we are right now. So that deals with his first law. Most of you, I would imagine here, are sitting comfortably still, either in your chair, at your desk, or maybe you're wherever you're at, enjoying a coffee in a cafe somewhere. Anyway, would you consider yourself moving in your present location, and how fast are you moving? So I'm assuming most of us, the majority, are probably going to say no, unless you're listening to this lecture on a bus or something, in which case you might say, oh, I'm doing 50 miles an hour, okay, or something like that. But none of us, I don't think, are going to take into the effect that the Earth is spinning us around through space. So that spins us at a large, at a great speed. Are we traveling that speed because we're on the Earth? Well, yeah, we are traveling that speed. But the Earth is also rotating around the sun. So are we traveling that speed? And in a way, yes, we are traveling that speed as well. And, our solar system is traveling through the rest of the universe, through the Milky Way galaxy at some other speed, some astronomical speed. And the universe is expanding at a speed. And we have all of these different speeds. So how fast are we moving is a very hard question to answer. So to do that, we need to come up with a law that states, well, this is what we're going to do, and this is where we're going to take our measurements from. Okay? So that's what Newton's first law is all about. It says that if an object does not interact with other objects, it is possible to identify a reference frame in which the object has 0 acceleration. So the reference frame is the key to the first part, right? There is some reference frame in which an object always has 0 acceleration. So think of an ant on a bow and arrow, on the arrow part of the bow and arrow, right? The arrow is fired and the ant clings on for dear life. Now, if we are watching that from our reference frame, we see the ant moving, right? We see that ant moving, getting accelerated from stop and wherever it goes, right? But there's another reference frame in which that ant isn't moving at all, and that would be if we were shrunk down and placed on the arrow with the ant. Right? Then we're on a different reference frame. We are with the ant. The world moves around us, and us and the ant are hanging on for dear life on this thing, right? But to each other, we're not moving. So that's kind of what we mean by reference frames. Okay. Okay. So part 2 of this says that within this inertial reference frame, within that frame, the acceleration of an object is proportional to force and inversely proportional to mass. I guess before I go too much further, I do want to state here on the Newton's first law, the alternative statement to it is one you probably know. And that's called, in the absence of external forces, when viewed from an inertial reference frame, an object at rest remains at rest, an object in motion continues in motion with a constant velocity in a straight line. Okay, so that's probably, you've heard of that. Object at rest remains at rest, object in motion stays at motion. That is Newton's first law. Newton's second law says that this force is proportionally scalable here. with mass and with acceleration. So this is the first time we're bringing mass up into this. Mass we talked about in the first lecture about its units, on how it's in kilograms. Acceleration we should know plenty about by now, on what the acceleration is. Mass is rather difficult to define. So there is numerous definitions in the books and other places, but I kind of like to think of it in simplest terms. And I define mass as the difficulty it is to move an object, to get that object to start in motion. And you'll see why I pick that definition later when we get into later chapters, because it's referenced to something else. But you can think of it that way, that if something has more mass, it's generally more difficult to get into motion. It's more difficult to accelerate. Difference between a baseball and a bowling ball. Okay, more mass, harder to accelerate it up. Okay, so that's how I would like to think of that, and that's how we come up with the equation of F is equal to ma, and we'll be using that equation a lot as we go through here. So F would stand for force, m is the mass, a is the acceleration, and that is the general equation for force. Now, these work in all three dimensions. I can have force in the x direction by using the acceleration of the x direction, and vice versa for the y and the z. So I can break those down into vectors because acceleration is a vector, so hence force is a vector. Mass is just a scalar, right? It just scales it up. So that's actually our second law. The third law, before I get to the third law, to try and give you a little bit more clarity on a Newton, 1 Newton of force is about 1/4 of a pound. Okay, so weight is a force. So if you think of a Newton roughly equal to 1/4 of a pound, for U.S. customary units, that's about where we're at. Okay. All right, for the third law, we have two objects that interact. The force will be equal and opposite in direction of each other. So this law is actually kind of worded, I find, to be a little bit weird. It states that if two objects interact, the force F12 exerted on object 1 by object 1 on object 2 is equal in magnitude but opposite in direction of the force 2-1 exerted by object 2 onto object 1. It's a little bit of tough to get a handle on that, so I've kind of just written down in here that the force will be equal but opposite in direction. So I'm sure that's kind of maybe how you've heard it in other books, other terms and stuff like that. But frankly, what it means is that we have a force, right? We have a force of these two objects, and 1 is going to be pushing on 2. Okay, force of 1 on 2, not a 12, but a 1 onto 2. That force is equal to the same force but negative from 2 onto 1, so they push, right? So if I put my hands together, the force of 1 on 2 is the same as 2 on 1, but in the opposite direction. All right, so they push together. Okay. And that's equal for a ton of different things. If you lean on a wall, for instance, you'll see that those forces equal out. The wall actually pushes back on you to hold you up, unless you can really, really push on something to get it to begin in motion. That force will be pushing back on you. Okay, so that I think covers Newton's 3 laws. We'll be covering, let's see actually what's next on here. We'll be covering how to do these force problems, how to work with them, and the first thing we usually do is do a drawing, right? So here we have the free body diagram. It's just more drawing. It's what we're going to do for the problem so that we can keep everything in order, see where everything is at, keep track of all of our forces, because there's actually quite a few forces. So when we draw out a free body diagram, it's just labeling all of the forces that an object would have, everything that acts on that object, and it's just there to make those to make it clear, right? Because a picture, I think, works a little better than words. To have to go back and continually reread the problem, to have it a picture right in front of you, I think is nice, is a little better. So you can see here we have an example of a biker going up an incline. We have the force that's applied. This biker here is pushing, he's applying a force in order to climb up this hill. We have gravity, force of gravity here is pulling down. I'm going to go over these in greater detail in the next slide. We have something called the normal force that's pointing upward here off of the surface. We'll have friction force. Friction always opposes you as you go up there, and they're all up in different directions. So the free body diagram, which is seen here, helps just label them out, maintain them, get them a little more clarity, and give us some more room for numbers. So that's why we do the free body diagram. Okay, we're going to start out with just a few of those forces, and then I'm going to add more in as I go through the problems. Some of the problems we will come into are going to be called equilibrium. Equilibrium just means that the total force acting on an object is zero. So you'll see these written as summations of the forces, where if we take all the forces and we add them all up, an equilibrium state would mean that they equal out to zero. This does not mean that those forces are zero, but rather that they cancel each other. So if this hand pushes with 5 newtons and this hand pushes with 5 newtons the other way, we don't see any movement because these two forces cancel each other. But that's not that they're zero. This is pushing with 5 newtons, and this one is pushing with 5 newtons. Examples of equilibrium: you have a light fixture hanging from a ceiling, like a fan or a chandelier or something. A truck moving at a constant speed. If there's friction involved, there could be equilibrium. You know, when you get in your car and you go down the highway or whatnot, you still have to have some acceleration in order to maintain your speed. And that's what that's doing. Is it's the engine is outputting power, it's outputting a force. That force is counteracting with the wind and the friction and everything else that's going on in the environment. Another example is your computer just sitting on your desk. Okay, why doesn't the computer fall through the desk? It has the force of gravity constantly pulling it down. And the reason behind that one is the normal force, which is the force of the desk pushing back upon the computer, stabilizes it, neutralizes it, sets it in a state of equilibrium. Those two counter each other constantly, and that's why your computer doesn't move or whatever it is that you have sitting on your desk. Okay. So common force names. So we have some terms, I guess, to get out of the way here. So one is an acting force. This is usually an engine, a train, a truck, or a person that is causing the force, right? Something has to be causing the force, the push, or the pull to occur. So that usually is what we call the acting force, where it is generated from. Usually those forces can just be written as F equals ma. They don't have a specific formula for an acting force. Most of the time I will put a subscript A next to the F so that you know that it is the acting force that's on it. And again, all forces can be written as ma in their basic degrees, so it's a good general equation to have that we can throw in when we don't have any other options. The gravitational force. So this is all objects on Earth. Gravity is pulling down on them. It's very similar to the F is equal to ma, except for we know that the acceleration due to gravity is g, 9.8. So we substitute g in there. So we have the force of gravity, which again I'll subscript with a lowercase g to denote that it is the gravitational force, and it's just mass times the 9.8, the acceleration of gravity. So that one we have a nice formula for. The normal force. This is what allows objects to stand or rest on a surface. So as I said, your desk, your computer, it sits on top. The desk pushes back on the computer and it balances out those forces. As we saw on the previous slide with the angle and the biker is on the road. The normal force is perpendicular to the road because the road is pushing back on the bike. If I were to push on a wall, the normal force would be from the wall surface pointing back towards me. It's what I'm pushing in, it's the wall pushing back. Okay, so that's the normal force, and we'll do a bunch of different equations that have normal force in them as well. There's no good equation for normal force. It's not like you can just plug it in and get it. It is problem specific. Okay. Then we have the friction force. Friction always works against you. It never works for you. So whichever way your object is moving, right? So it depends on the direction of movement. If you have something that is moving to the left, friction will point to the right. If you have movement to the right, friction will point to the left. If you're trying to climb, if you're trying to bring something vertically, you're trying to raise up against a surface, it will be pointing down, just like in the bike example again on the previous slide. The biker is going up the hill, friction is pointing down the hill. It always opposes the motion. Friction force does have an equation. I will denote it with a lowercase subscript f. So you'll have force of friction, so you'll have capital F with a lowercase subscript f for the friction force. And it's equal to this Greek symbol mu, which there's a couple of different flavors for mu. You can have static mu or you can have kinetic mu. I'll go over those in one of the examples. I think it's example 4 or 5 on the different types of mu. But the equation remains the same. Even though there's 2 different types of mu, you just have to know which problem you're working with. And then it's multiplied by the normal force. Okay, so it's a force on top of a force. It's a scaled version of the normal force. Because the normal force is the object that is pushing back on whatever your object is that is moving. So if it's a table, the amount of friction that you have between your object and the table depends on how hard the table has to push back on your object. If those two don't touch, there's no normal force, there's also no friction because there's no touching. Okay, so we'll do a couple of examples with that as well. And then the last one here is the tension force. They use tension in a lot of other examples with ropes and cables and pulleys. Tension is basically just an extension of force by means of a rope, right? So it might not be direct, a direct force, like somebody actually pulling on it, but we can use a rope to tie different masses together, which I think is example 5 maybe. We can use ropes and cables to tie all those things together and kind of extend our forces, make an extension of the forces. Okay, so that's your new vocab words, your new, there is a lot of them. We'll actually gain a few more as we go through the chapters, but this is a good starting off point. There's a lot of examples for this chapter. It's a very long video, so hopefully you stay tuned and we will go through everything, every possibility, and get you a little bit better idea on how these forces work and how to solve these problems. I got some examples here for chapter 5. So this one's all about forces. I've got the forces written up. This is the general equation for forces. F is equal to ma. You can use this for pretty much every force. You just have to adapt it for the situation. So this is where they're all constructed from. The force of gravity, we can go ahead and shorthand this one because we know the acceleration is g, so we can replace the a with the g and get the force of gravity to be mg. The normal force, there is no equation for the normal force. We denote it with an f and a lower, or an n, subscript n. For the normal force, we'll describe a couple things on the normal force as well. And then there's the friction force, and that has a couple of different values for this mu. You can either have static mu or you can have kinetic mu, depending on the type of friction, whether the object is moving or not. And then that is closely related to the normal force, so we'd have to go back to the normal force to solve those equations for friction. So they're all tied together. I'm going to start off with something very basic where we don't have to do much. We can kind of just get an idea on how these equations work and what they look like. So equation 1's pretty simple. We have a plane here. The plane's engines can produce 37,000 newtons of force when accelerating. So aviation would call that thrust for the plane. It's the accelerating power of the plane. It's the push of the engines to get it to move. The plane has a mass of 31,000 kilograms. What is the acceleration of the plane? Okay. So the acceleration of the plane is what we're looking for. We're looking for an A and we're given an F. We go up to our equations and we look at what is related, and we can see that the general equation F is equal to ma would have everything that we would need. Okay, F equal to ma. So the plane's engines produce 37,000 newtons. The mass of the plane is 31,000 kilograms, and we need to solve for A. So if you punch that in, you should get an acceleration of 1.1. Let's just go 1.2. We'll do 1.194. That's fine. That's what I've got written down there. I'm hoping that that's right. And it's an acceleration just like every other acceleration. It has to have meters per second squared. So you see, for the first part, nice and easy, quick example, acceleration of the plane, we can find acceleration. You'll see these tied in quite a bit with kinematic equations, where you get the acceleration from force, and then that gives you your third bit of information for kinematics. Then you can solve more kinematic equations. In this one, though, we have a part B. It says here that a pilot inside has a mass of 78 kilograms inside the plane, right? The pilot. What force does the pilot feel? Do they feel 37,000 newtons of force because that's what the plane has? No, right? So if you look at Newton's laws, you get Newton's laws, you see that different masses are going to experience those different forces. They're all proportional to that acceleration that's inside. So to figure out what kind of force the pilot feels, like the G force or whatever you want to call it, of them going being pushed back in their seat as the plane takes off, we can figure that out. Now that we know that the plane has an acceleration of 1.94, we can look at what the pilot experiences with that same acceleration, since he'll be in the plane, or they will be in the plane. So for this, it's again F equals to ma. Okay. This time we're looking for the force. We're given the mass of 78. And we know that the whole system accelerates at the same speed because the pilot and plane are together. So the whole thing is going to accelerate at this 1.194. Okay. And if we take that, we see then that the pilot should experience a force of roughly 93.13. 93.13. That's just newtons then, newtons of force the pilot then feels. Yeah, so that's a simple one. We can kind of demonstrate a little bit of Newton's laws, how we have the proportionality in check, the relation in check, and just a basic example of force. Okay, so we'll move on. We'll do a couple little harder ones here. I decided to do a box example for number 2. This one I don't have enough board space for all the parts, so I'm just going to kind of do it and erase it as I go here. So this one's going to continue on for a little while. What we have here is a box. It weighs 10 kilograms, and it's being pulled by a rope. This is the basic example, and then we're going to adapt this problem. We're going to add more things into it for the other parts. There's part A over here says the box is pulled from rest with 20 newtons of force horizontally. What is the velocity of the box after 3 seconds? So it hasn't mentioned anything about friction. It hasn't mentioned anything about an angle. It says it's horizontal. So these things we can assume are what they are, that there is no friction. It's frictionless because it's not mentioned. It didn't give us a mu, anything like that would pertain to friction. So with these examples here for force, it is good to draw a free body diagram. The first one didn't quite need it because it was just a plane and it was one equation and it was pretty simple. Now we've got more stuff going on. So it's easy to draw a free body diagram. For this box, it's going to start off to be pretty plain, and this can be whatever it is, okay, whatever the object is. In this case, it is a box, but if the example was a plane or a car or a cat or a person, you can draw them as whatever you'd like, okay? And what I want to do is I just want to list out all of the forces that are acting on that object. All right. So I know that there's always going to be a force of gravity that is pulling something down. So that's Fg. And I have an equation for that I know is mg. So gravity always pulls down. That one's kind of a given in most equations, right? You'll have that force of gravity pulling down. But this box isn't falling. It's sitting on something, a floor. It's being dragged across horizontally. So there's another force that's taking place. Something has to counter that gravitational force. And that's what we call the normal force. Okay, so that must point up in order to counteract that gravitational. It's always the objects, they call it the normal to the surface. It would always be perpendicular to that plane that it is resting on. So in our case, it's horizontal. We're going to go ahead and have the normal force being vertical then, straight up because of that plane. There's one more force that's taking effect here, and that is the rope is being pulled. That creates another force. That's the acting force. But because it goes through a rope, it's traditionally given a T for tension. Tension in the rope. You can also list it as an acting force. Acting force usually means that it's direct. Being this one's a rope, I'm going to leave it as T for tension, but you'll get the same answer either way, no matter what you call the variable. Okay, so since this says the box is pulled from rest with 20 newtons of force, so I know the amount of force that is being pulled, I need to find something with the velocity of the box after 3 seconds. I go to my force equations and I don't see anything up there that says it has to do with velocity. And the only thing I know that has velocity, and they gave a hint of time, is the kinematics. Okay, at this point in the class anyway, that's the only thing that we have. So let me try and solve it with kinematics. Maybe that's what we need to do. So on this side over here, being it's all in the x direction, I just have to do a delta x, a vi, a vf, an a, and a t. Okay, so this is like last chapter. Okay. Now, what can I pull out of that question? Well, I know that the box says it's pulled from rest, which means it initially started with a 0. So the initial velocity must have been 0. What is the velocity of the box after 3 seconds? Okay, so what the question is asking for is what is the final velocity if time is 3 seconds? Okay. So I only have 2 bits of information. I need to find a third bit. And the reason that it gave me the 20 newtons of force is so then I can find the acceleration. Just like in the previous problem, we can find acceleration that way. Okay. So what I'll do here, I'll hop over here. I know that it's being pulled with 20 newtons of force, so I'll have F is equal to ma, our generic equation. This I know to be 20 newtons. The mass is not given in the problem, but it's given in the drawing. So I will have 10 times A, and this is going to tell me that A is equal to 2 meters per second squared. Okay, so now I can take my 2 meters per second squared, and I can plug it in over here for the acceleration. And now I've got my 3 bits of info that'll let me solve for VF. Do you remember which equation didn't care about the delta x? If you have to go back, go back. Or look at the equation sheet and figure out which one does not deal with delta x. It's the first equation. VF is equal to VI plus A times T. Okay. So VF is what I'm looking for. So I'm going to leave that one alone. VI is 0. That's perfect. Plus A. A we calculated to be 2. And the time is 3. So what's our VF? 2 times 3 is 6. And there's our final answer. We put a box around it. We have our units. 6 meters per second. Okay, so you can see now how this new chapter relates to the old chapter. We can gather some information from the new stuff and relay it into the old stuff. There will also be like a very easy part B to this question if we wanted that would ask for delta x. And maybe you want to run through those if you're having trouble with chapter 4. Maybe you want to run through and solve out for delta x. Be just more kinematic equations on it. Okay, so I'm going to pause here for 1 second. I'm going to rewrite the next part of this question because the board's already getting full. And we'll do a little bit more with this box example. Okay, so now we're getting this one a little bit more involved. Part B of this now says to assume the box is moving over a rough part of the floor. So I've now drawn a squiggly there for some rough floor that it's going to be dragged across. It is still being pulled with 20 newtons of force, but the speed is a constant 6 meters per second. So there must be something that's slowing it down. It's the friction force. It asks us to determine the friction force on the box and its coefficient. Okay, so the friction force would be the friction force here, and the coefficient is its mu. That's the coefficient of friction. Okay, so we go back to our free body diagram. That's always where we want to start with these things, is go back to our free body diagram. Gravitational force is still in full effect, okay? The tension on the rope, it's still being pulled horizontally, so we don't worry about that. That stays the same. The normal force remains the same. It's counteracting the field that it's on, so it's pointing up. But now there's a new force, the friction force. And that friction force must be pointed backward because it always opposes the motion. And if the box is going this way, friction will be pointing the other way and it will be fighting it. Okay, so we have now added a new force, which means we're going to have to do some new stuff. This is actually what we're looking for, is that friction force. So how can I go about this one? Okay, well, kinematics aren't going to do me any good anymore because I'm not asking for velocity or anything. I'm looking for forces. So I need to ask myself a couple of questions when I come to these problems with forces. And one of the things you can usually do is look at the sum of all of the forces. So to do that, we have two different directions going on. We have X and we have Y. So I would like to determine what the sum of the forces are in the X and what the sum of the forces are in the Y. So this is a summation. It just means the overall. If you took everything and summed it all together, what do you get for the number? Okay. Common in math. What I want to do here, I like to do it in kind of a little reverse order. You might do it in original, it doesn't matter. I like to list out my forces in each of the directions and then determine whether or not that sum is a number or it might be zero. So what I'm going to do is I'm going to look at the two forces that are in the X direction. And I've got T, tension, which is heading off in the positive direction. So I'm going to put a tension down as being positive. That's one of the forces in the X direction, and it's positive. I see the friction force, that's pointing backward, so it's in the negative direction. So I'm going to add that one in as a minus the friction force. Okay. And that takes care of the two forces in that direction. Now for the Y direction, I have the normal force, which is pointing up, so that will be my positive. Okay, positive normal force. And then I have Fg pointing down, so I'll go minus the force of gravity. Okay, so now I've summed everything, I've drawn everything out, and I've got them all where they need to be in their order, and now I ask myself a very important question. And that is there any overall acceleration in these directions? Because if there's an acceleration, there'll be an overall force, okay, in either the X or the Y. So I look at the problem and I go, okay, is there any acceleration that is occurring in the X direction? And in the first part, part A, absolutely there was. In this one, it says that it is a constant 6 meters per second. Well, if it's a constant speed, it has no acceleration. So I know that the sum of the forces for the X is equal to 0. So you might want to just add a 0. I like to change it like this so I have a nice equation. And this is the thing that I'm looking for, is FF for the part for the first part, determine the friction force. So let's see, if I take this top equation and I add friction force to the 0 on the other side, I will get that T is equal to that friction force. What is T? Okay, T was given in the problem as still being pulled with 20 newtons of force. So this friction force, I know, has to equal 20 newtons. If T is equal to the friction force and T is 20, then the friction force must also be 20. So they're balancing, they're canceling each other out. You can see tension being pulled with 20 newtons here, friction force being pulled with 20 newtons here, and that's why we have an overall 0 acceleration. But that's just the first part. Determine the friction force on the box. Now it wants its coefficient. It wants that mu. Okay, so I go back and I look at my equations and I find where is this mu that I need to solve for. It's in the friction force equation. I have that friction force is equal to mu times the normal force. Okay, so now I'm looking for this mu. I know what the friction force is. It's 20. I solved it in the first part. So I have 20 is equal to, now here's what I need is that mu. How do I find the normal force? There's no equation for it. Okay, so a lot of students get a little stuck on that one. How to find the normal force. Just like we did with kinematics, look somewhere else. Go back through your work and look through. Where does the normal force pop up? Pops up over here. So let me see if I can do anything with this equation to solve out for the normal force. I ask myself the same question that I did with the x. I'm asking it with the y. Is there any overall acceleration in the y? Is that box moving up and down, jumping around, or falling in the y direction? Now it's being pulled on a horizontal floor. There is no acceleration in the y. So this acceleration, that force, will then go to 0. Okay, same trick I did up here. If I add Fg to the other side, I will get that Fn is equal then to Fg. Well, what's Fg? Fg has an equation, right? Fg is nice and easy. Fg is equal to mg. Okay, now I'm getting something. So I have the normal force is equal to mg. I know what m is. It was given in the problem. So m is 10 and g is 9.8. So I can multiply 10 by 9.8 and I will get that Fn is equal to 98 newtons. Okay, but that's not our answer. We need to plug this Fn in over here. We need to solve for mu, so never lose track of where you're trying to solve. That normal force is 98. I need to plug that in over here for Fn. And now I just have to do a little bit of math. I didn't prep this one ahead of time, so I'm going to grab my calculator and just do 20 divided by 98. And we get something around mu equaling 0.2. We'll go with that. Now, what are the units for mu? How do I put the units down for mu? Well, I look at the equation and I go, well, force of friction, all forces, anything with the word force in it, is in newtons, right? So if the force of friction is newtons, equals to this mu, and the normal force also is newtons. If I divide that over, I'm going to get newtons over newtons. Well, newtons over newtons is just 1, which means mu is just a coefficient. It doesn't have any units. It's just a coefficient. So mu is one of the unitless variables that we solve for occasionally. Okay, so that one was a little bit harder. Okay, it was a little bit more involved, but you can kind of see where these are going. Hopefully that was enough of a slow progression here. Okay, I'm going to change it up again for part C. We'll have a little bit of a different problem going on, and we'll see if we can make it a little bit tougher. Okay, get you some more examples. Okay, part C. Getting more difficult here, more challenging. So now we have changed the angle at which you're pulling the box. You're now going to try and give it an upward angle. Try and ease yourself by pulling upward as you pull it across this rough surface. So your upward angle is now 45 degrees. The friction coefficient remains the same. We found it to be 0.2, and that's going to remain the same in this problem. You've also increased the pulling force to cause 30 newtons now of tension. Okay, you're hoping to accelerate that box and have that box start accelerating up again. And that's what we're trying to find. We're going to try and find the acceleration of the box. Okay, so again, we need to redo our free body diagram now that things have changed. So I will draw out our free body diagram. Some of the forces we can list right away. We still have the force of gravity always pulling down. We will have this pulling force now is at an angle. So what do we do when things are at angles? Right? If I'm going to break this down into x's and y's, I need to break that down into x's and y's. Okay, so hopefully here we have enough understanding from the previous chapters that we can take 30 times the sine of 45, 30 times the cosine of 45, and get our x and y components of that tension. So I'm going to have some tension here. Tension would be 30. Let's see, so for the x, it would be adjacent, so we'd have the cosine of 45, and that gives us 21.2. Okay, 21.2 newtons that way. The tension that is going upward, because this is going forward and upward, tension that's going upward would also be 30 times the sine of 45. And that would be the same, 21.2 newtons, just because it's a 45-degree angle. Okay, what other forces do we have? Well, we still have the normal force. Okay, that's going to point up. We still have that going on. And we still have friction that's in play. And the friction always points opposite of the motion. So we have friction over here. Okay, so you see how they're getting a little bit more. Now that we've got so much going on, now it's really key we go ahead and do our sums. So let's... Sorry, my camera died here, so I lost part of the problem. But we'll pick up right where we left off. I've redrawn it here with the block, 10 kilograms, the tension moving, and I believe we were right here when the camera died. We were just summing up the forces, or just ready to sum up the forces. And all I want to do is just go ahead and write down which ones are here. So in the x direction, we only have two forces. I have the tension force at which we are pulling. Now it's not the full 30 newtons because we're at a 45-degree angle. So I'm going to list this as 21.2 newtons because that's the amount that is in the x direction. And the only force that opposes this is the friction force. So I'm going to minus the friction force. Instead of writing friction force, I have an equation for friction force. Okay, I have mu times the normal force. So I'll write down that as the friction force. So I'm making little steps to keep the videos a little shorter. Hopefully we can keep up on this, but feel free in your homeworks to write out, or in your notes to write out every single step if you wish. Okay, anyway, this is the two forces in the x that takes care of that. Now on the y, I have three forces, so I'm going to go ahead and write those in. I have two of them pointing up. I have the normal force, and I have tension. And tension in this case is 30 times the sine of 45, just happens to be the exact same as in the x. Don't always assume that. It's only on a 45-degree angle. So these two point up, so they're going to be both positives. The one that points down is the gravitational force, which I can write as mg. Now, I have to ask myself the questions. Okay, where is the overall acceleration? Where is the overall motion that is occurring here? And there needs to be an acceleration in order for there to be a force. So the problem states that we're trying to determine the acceleration. If you were to think of this problem in real life, if you were pulling this box across a bumpy road, or you're moving into a dorm, or you're something, trying to get something into down the sidewalk, right? You might be pulling upward with a 45-degree angle on some kind of a rope or a chain or something, or you're taking your pet for a walk. I don't know, whatever. All right. If you pull on that rope or that chain, what do you think is going to happen? Is it likely that the object will move along the sidewalk in the direction that you're traveling? That would be the normal reaction. You would not expect the object to bounce up and down. You're pulling upward slightly, but not nearly enough to make the object jump up off the surface and pull it that way. That would be much more direct tension upward to lift it off the ground, right? So I can assume that the sum of the forces in the y direction are 0. But I cannot make that assumption for the x, right? If there is going to be some acceleration, it will be in the x direction. So let's see if I can solve for it, right? Can I solve for the overall forces in the x direction? I've got 21.2, just a number. I have mu, 0.2 from before. All I need would be the normal force, and I could solve for that overall force. So let me solve for the normal force. And like the previous one, I'm going to go to the next equation to try and solve for it. So now I see the normal force here, and we have something equal to 0, which means I can move these parts to the other side and solve for the normal force. If I do that, I'm going to have this negative mg getting added to the other side, which is going to make it positive, so I'll have an mg. And then I'll have this 21.2 being subtracted to the other side. So I'll have a negative 21.2. Now I know mg. I can go ahead and fill that out as well. Normal force is equal to, the mass was 10, g was 9.8, which means the normal force, okay, is just an easy set here that we can punch into our calculators and solve out. All right, so 10 times 9.8 gives you 98. 98 minus 21.2, plug it into your calculator, should give you 76.8 newtons. Okay, almost boxed the answer. That's not our answer. We're looking for acceleration. I need to plug that normal force into the equation up here. Okay? Because remember, I'm trying to find acceleration. So where can I find the acceleration? Well, this is the sum of all the forces. Okay? And if we take all forces are equal to ma. So I can get an acceleration from that. So I'm going to replace summing everything to fx and change it to ma. Okay, so this is the sum of the forces. If you want to say it's the sum of the forces in the x direction, you can do that as well. I had a professor do that. Okay, so this is our sum of everything in the x direction, and it's equal to 21.2 minus, so I'm just grabbing the rest, this is now ma, 21.2 minus mu, which is 0.2, times the normal force. And the normal force we had just solved to be 76.8. Okay, so the 76.8, excuse me, we'll see that this is actually smaller than the last problem that we did, right? And it's because you're alleviating some of the friction by pulling up on the box, right? The box isn't so heavy, if you want to say, onto that frictional surface. You're putting some tension, you're pulling up on that box, and you're alleviating some of that friction. That's why this number is actually less. Okay, so that should conceptually make sense. Okay, so m, I know what m is. That would be 10. Okay, this will give me all of my a's, 21.2 minus, and then whatever this number is. So here we're just going to plug into our calculators. All right, here we just plug into the calculators and we find our acceleration. This will end up just being a large number. We take that, we divide by 10. Well, not even a large number. And you should get a good acceleration. So do that out on your own. See if you can get the same answers that I have. We have 0.584. And that would be meters per second squared. Okay, it is slower than what we initially found in part A. Well, because now there's friction. At one point we had no acceleration because we were in such a bumpy part of the road there. We increased our tension. We gave it more pull. We pulled it up at a little bit of a higher angle, a 45-degree angle, alleviated some of that tension from some of that friction, and we ended up back with an acceleration, a positive acceleration. So it's a slow acceleration, but it's there. Positive acceleration, so the box will now accelerate, continue to accelerate forward down that path. Okay? So hopefully that makes sense. And now you can see, you can easily tag on an extra problem on here for kinematics, saying, well, now what is the final velocity after so much time has passed? Or maybe the friction surface is a specific displacement. Maybe it travels 20 meters over this displacement. I could ask you questions on that, how much time passes, or velocities, or you can see now how I can relate this back to any of those kinematics that you have previously learned. So we're expanding the amount of questions I could ask you. Okay, that's what it is. You expand your knowledge. Okay. All right, we'll do a little bit more on this box before we move into anything else. So I'll reset up the board. I'm going to try and find a different marker, and we'll be right back. Okay, so we're back with our box. We've now pulled our box up an incline, up a slope. Okay, so we're now out of the mu is equal to 0.2, the rough surface. We found this ramp, and we have pulled it up that ramp to a height of 1 meter. Now, the ramp's at a 20-degree angle, and it has a different mu. That friction coefficient is 0.05, so it's a much slicker surface. It has a smaller mu, so friction will take less effect. You pause there to take a break. You've done a lot of work. You're tired. You pause to take a break. You let go of the box. The box slides back down the ramp. How long does it take for the box to get to the bottom of the ramp? So it's asking for time. How long does it take for this box, once you let it go, to slide down and reach the bottom of the ramp? Okay, so this is a pretty involved one. Okay, maybe you can kind of see where we're going with it. Do the same steps that we always do. Let's draw a free body diagram. Okay, so now my box is at an angle. Okay. I, of course, have the friction, or the gravitational force, right? Pulling down, the weight of the box. That always points straight down. Okay? It's equal to mg. I no longer have tension. I have let go of the box. The box is now at rest at the top. I no longer have any tension, so I don't need to worry about that. I do still have the normal force. Okay, so the normal force on this, make sure we understand the normal force. The normal force is always the normal of the surface that it is on. Okay, so the normal force here is not going to point up. It's going to point at about 20 degrees. Okay, because it's at a 20-degree angle. Okay, so it'll point over like that for the normal force. Now there's some friction. Okay, there's friction involved because there's a mu. Which way does that point? Well, in all of our other examples, it's on the left because the box was moving to the right. This example, the box is going to come sliding back down the ramp. So friction force must always oppose the motion. So the friction force is going to go on that side. Okay. Now what can I do with this? All right. I've got an angle in here, so I've got to break some things down, and there's a couple of ways of doing it. Both the normal force and the friction force are at 20-degree angles. Okay, the gravitational force is the only one that's pointing straight down. But these are all vectors, right? All of these are vectors. So what can you do with vectors? Well, I can set it up so that the entire XY plane is at a 20-degree angle. So X, Y. Okay, so you can also break all of these other vectors down by 20 degrees But as we've seen in the previous example, you might have 4 or 5 different forces that you're going to have to break down. It's actually easier and it's traditional to just move the plane so that you have to do less work. If we look at the x and the y-axis at a 20-degree tilt, then the normal force is perfectly in the y. The friction force is perfectly in the x, and the only one we have to worry about is the gravitational force. Okay, so which means I'll need to break that gravitational force down. Okay, well, what's the angle on the gravitational force? Okay, some simple mathematics here. If this was coming straight down, this angle here is that same 20-degree angle that we're seeing over there. If you need to kind of convince yourself of that, imagine having the block on there, right? And the gravitational force coming straight down. Then rotate that block 20 degrees. You'll see that the gravitational force will then also come over 20 degrees. And that's how we're getting that 20-degree angle in there. So hopefully that makes okay sense. So what I want to do is I want to break that gravitational force down so that, let's see, it's going down and forward. So there's going to be a downward angle here component of it. And there'll be a small forward angle, a small forward component of it. Okay. So instead of this, I want to have the two components, one going down and one going forward, so that I don't have this. Okay. Now I know that the hypotenuse is mg, or 10 times 9.8, or 98. So I know the hypotenuse of that triangle is going to be 98. How much is going to be each of the components? Well, we do our trigonometry again, right? So this is the adjacent, which means it's going to be the cosine. So this is going to be 98 cosine of 20. This is the downward y direction, so that would be this one. This is the negative x direction. This is opposite, so we're going to have 98 sine of 20. All right, so let's plug those in. Let's see what we get when we do those. Okay, so I'll start with the cosine. We'll do 98 cosine 20 degrees, and we end up with 92, let's just call it 92. 92 newtons here. Okay, that's the downward, the y, okay? 92 newtons down. Let's do with the negative x, so that's going to give us a 98 sine of 20. 98 sine of 20 gives us a 33.5. Okay, hopefully that makes sense. We are getting in depth here. Okay, now I've done my little trig. I'm going to save some board space. Go ahead and get rid of this. I've done the trig. Trig should be second nature by now. You've probably done enough of it where hopefully you can do that. All right, so now this whole thing is just written at a slight angle, but everything is either in an x or in a y. It's all in the correct direction. So all I have to do now is look for fx and fy sums. All right. So now the fx, I have a couple things in here. One, I have the friction force, which is now pointing in the positive direction. So I'll have the friction force. And I have this fg pointing backwards. So this is going to be a minus 33.5. Okay. In the y direction, I also have two. I have the normal force, which is pointing up. And I have this component of fg, which is pointing down, 92. Okay. You might be going, well, where are we going with this? How am I going to find the time it takes for the box to get down the ramp? That's all back on kinematics. That's where time comes into place, which means I need to find the acceleration of the box. Okay? Now, we ask ourselves, what are these numbers? Do we have positives? Do we have zeros? Do we have negatives? What do we have? Okay. This is now our y direction, is this angle here, right? Is that box going to jump up and down, up off the ramp? No. Which means this is a 0, right? There is no acceleration in the y to be had. But there will be acceleration in the x direction. So remember, the x direction is this way. And if the box is sliding, this is the direction it'll slide in. Okay, so there will be something there. So it's similar to the last problem. This I can write as ma to figure out what the acceleration is. So let's go ma is equal to, the friction force can be written as mu times the normal force. And that 33.5 will just carry over minus 33.5. I need to solve for the normal force here. If this is equal to 0, what is the normal force? Normal force is 92. So this one made it nice and easy to find the normal force. Okay. Now, we can take and we can plug in over onto the other side, see what we can plug in. So m, that's still our normal 10. A is what we're trying to solve for. Mu, our new mu, okay, we can't get those separate. Our new mu is 0.05. The normal force we have solved to be 92. And minus 33.5. So here we just have to figure out what A is equal to. Okay, so I take my calculator and I'm going to start punching in 0.05 times 92 minus 33.5, and I get a negative number. I get a negative 28.9. That needs to be divided by 10. We'll bring the 10 to the other side. Overall, we get a negative 2.89. And that's our acceleration. It's a negative acceleration. That should make sense. Negative acceleration because it's traveling in the negative x direction, right? It's falling back in the negative x direction. Negative 2.89. Now we can take that and we can run it into our kinematics. Okay? You were pulling up your box, you stopped to rest, which means you stopped the box. Initial velocity was 0. Final velocity, we don't know. Acceleration, we do. That is minus 2.89. And time is the thing that we're looking for. All right, so I'm missing something, right? It didn't state how fast the box was going to come crashing down at the bottom. I don't have a way to solve for velocity with forces right now, so that's not going to work. But it did tell us that the box was at a height of 1 meter, so maybe I can find displacement. I need to figure out how far the box fell. I need to know what this distance here is. Okay. How would I find that out? Well, it's another triangle. I have a 20-degree angle. I have 1 meter on one of the ends. It's the opposite end. Okay, so what would that be? Well, opposite would mean sine, right? So if I had the sine of 20, or SOHCAHTOA, sine of 20 would be the opposite, which would be 1 meter, over the hypotenuse, which is what I'm trying to find. Okay, because that hypotenuse is going to be the delta x here. It's going to be how far the box traveled down the ramp. Okay, which means the hypotenuse is just 1 over the sine of 20. All right, we can do that. Just plug it into your calculator. 1 divided by the sine of 20 gives you 2.9. Gives you 2.9. I'm just going to put it up here. 2.9 meters. That's our delta x. That's how far the box traveled, because it says how long does it take for the box to get to the bottom of the ramp. So I want it to go from the front of the box to the bottom of the ramp, 2.9 meters. Okay, all right. Let's see, we're going to go ahead and make that negative because it's traveling in the negative x direction according to our offset xy axis here. And now we can plug in. Okay, and now the thing that we don't care about is VF. Okay, do you remember which equation to use that doesn't involve VF? We have one that says delta x is equal to VI times t plus 1/2 AT squared. And that has no delta, or that has no final F in it. So we'll be able to go ahead and plug in. We have a negative 2.9 equals 2. This is a 0. 0 initial velocity makes the whole thing 0. Plus 1/2. This is also a negative 2.89. And we'll be solving for t. Okay, so hopefully you've done enough of those. I want you to go ahead and get some of that punched into your calculators. See if we get the same answers. And finally, I'm getting there. We should have a time of around 1.4. We can call it that. 1.4 seconds. Okay, hopefully you got there. I went ahead and did 1/2 times the negative 2.89. That got me a 1.445. And then I did the negative 2.9 divided by that negative 1.445. It got me an answer of around 2, and then I took square root of that because it's t squared. So that got me 1.4 seconds. And does that answer make sense? A box sliding down the ramp in about 1.5 seconds? Yeah, sure. That would make sense to me. That would be all right. It'd be an all right answer. So this one was really in depth. We had changes. We had little tricks that we could use that you can find in other problems. Lots of work to do, but you can also see now how this could expand into even more questions. For instance, there might be a follow-up that if this box then when the box hits here, it now slides across this floor, right? Which means you'd have to find out what the final velocity is here to find the initial velocity starting on the floor, and then it might ask, well, how far does the box slide before coming to rest? That's a great problem that you can do on your own. See if your answer makes any sense, right? The box, you can picture it in your mind. The box is going to slide down. It's going to hit this higher friction surface, and it's going to slide over and come to a stop somewhere over here, not very far. But there's something you can do if you want to do it on your own for more practice. We can ask how much time it takes to stop after that. I can change these parameters around into other things. There's endless possibilities for the questions we can ask. Okay. Hopefully that makes sense and it gets you a good idea on how to approach these. Okay, for example 3 here, I just want to go over the different types of friction force that we might run into in the problems and in the chapters. There's 2 different types. There's one called the static friction and one called kinetic friction. So static means that nothing is moving. It's static. It's solid. It's nothing going on. Kinematic, of course, means motion. It's what we have with the kinematic equation. So you have kinetic friction, which would be moving friction, and you have static friction, which would be solid friction. So I just want to go over those 2. In this example here, I've got a small child pushing a trash can. Trash can's even bigger than they are. Trash can weighs 5 kilograms. And the question asks how much force is needed to get the trash can moving. Okay. If we look at the friction force equation, we can have, well, let's start off with what we normally do, I guess, our free body diagram. We'll have Fg pointing down. We'll have the normal force just pointing straight up because we're keeping it simple for this one. And this child is going to push on the trash can. So their force will be in this direction. And we can just call it the acting force. And what is going to oppose that is going to be the friction force. Okay. Now, this is the setup that will be for both of the problems A and B here, so we can keep that up there. But there's just slight differences in the amount of force that is needed. So the first one, how much force is needed, we need to come up with our Fx and our Fy. Okay, summing up all the forces. If I look at the Fx, I have the acting force and the friction force. If I look at the Y, I have the normal force and the gravitational force. So these ones should be pretty simple to pop in now. Now, it says how much force is needed to get the trash can moving. So we're assuming now that everything is stationary and we're trying to get the trash can to move, right? The child is pushing on the trash can and they're pushing to the point where it just begins to start moving. That gets it moving. So to find that, it's wording in the question. It's sometimes tougher to quite get, but that's what we want. Is we want to figure out at what point does it just start to move. Okay. So my sum of the forces in the Y, of course, would be 0. The trash can is not moving up or down in the Y direction. And what I want to do here for the Fx is I don't want the can to already have an acceleration. I want the can to just begin moving. Okay, so far the can is not moving. So I'm going to give this a 0. Okay. The acting force is the force that I'm looking for. How much force do I have to apply to it? Well, if this is equal to 0, I can then say that the amount of force I need to apply is just equal to the friction force, which would be mu times the normal force. Now for this, the can is not moving. This needs to be the static mu. Okay, it needs to be the static mu because the can isn't moving yet. Which means I'll need to use the 0.1 that's given here in the problem. The normal force, we go back, we go, how do we solve the normal force? We can say that the normal force is equal to the gravitational force, which is equal to m times g, which is equal to 5 times 9.8. Okay. That'll give us a 49. So let's see. So the normal force would then be equal to 49. We can then take and we can start plugging into here. Okay, so the acting force, the force that we need, the acting force here, would be equal then to our static mu, which is 0.1, times the amount of normal force, which is 49. So we can see here that the acting force required on this one is 4.9 newtons. All right, so up here I can put Fa is equal to 4.9 newtons and give that a box. Okay. Now, when we move on to part B, it says once it is moving, how much force is now needed? Okay. Do you think it requires more force or less force once you get something moving? If you have dealt with this in real life, you'll notice that there's even a little saying that, like, well, if you can at least get it started, things become easy, or you're gaining momentum, or any of those types of things. If you can break that static force, that static friction force, if you can break that, the mu coefficient actually goes down, and this is a real thing that occurs. The mu goes down, decreasing the amount of friction. And it just stems from the fact that when it's static, it's really locked into the surface. Once the static friction breaks, it now kind of can glide along the surface and it's not so stuck in. So that kinetic friction allows it to move a little bit easier once moving. So we would expect our force to actually be less. Okay. And what are we going to do for that? Well, we go back to it and we say, well, there's still friction force, there's still the acting force, the normal force, everything there is the exact same. The normal force is still equal to mg, that hasn't changed at all. The only thing that has changed is that coefficient, right? So I go back and I say, well, the acting force must still be equal to mu times the normal force, but now I use the K version. It is moving, it is kinetic. Which means instead of the 0.0, I'm going to use 0.0 Sorry, instead of 0.1, I'm going to use the 0.07 times the normal force of 49. And now we can see that that number has gone down. It has gone down to 3.4. 3.43. Okay, and that's our new acting force, 3.43 newtons. So it actually is a pretty good difference, between the two, just by having that object moving. And there's tables if you want to look in books, look them up online. There are all sorts of tables for different materials, and it'll tell you both the static and the kinetic coefficient of friction. For instance, the tires on your car. If you're driving or anything like that, you'll notice that most of the time, hopefully, it is in a static state where the tire and the road are not moving. The tire stays stuck onto the road as it drives down. As soon as you lose traction and that wheel begins to spin, it doesn't regain that traction again unless you slow down. You have to slow down quite a bit in order for that tire to grab again onto the road. And it is because you have broken this state and gone into this state for friction. And you need to slow down enough. You need to reduce the force, reduce the motion, reduce everything down so that that static can take back over again. And you'll get traction again. Okay? All right, so hopefully that made sense on friction force. Just want to do a quick example of the two. They're normally going to be given in the problem, whether it's static or friction, or it'll say, for instance, like this, the trash can is at rest, or something along those lines. Okay, so for example 4, I want to dive in a little bit deeper on tension. Here we have a collection of masses, all connected by ropes. So it's the first time we've had more than one mass. So I want to show you how to do these problems as well. So at the end here, we have a 2 kilogram mass. It's connected to a 5 kilogram mass by a rope. So there's going to be a tension in that rope, which I've just called T1. The 5 kilogram is connected to a 10 kilogram mass, and there's a rope in between those. So I'm going to call that rope T2. And there is a rope connected to the 10 kilogram mass that is connected through this entire thing, and we're going to call that T3. Now T3, there's a force out front here, an acting force, of 100 newtons that is pulling this thing along. Okay. Now we're going to go ahead and assume that this is just frictionless, just to make things easier for the example. You've seen in the previous videos, we could add friction in, and it just adds an extra element to work out the problem. So I'm hoping that if I do give a hard problem like that with some friction in it, that you're able to go ahead and solve that as well. But let's assume that there's no friction. Let's just go ahead and assume this is a frictionless surface. And what I want to do is try and figure out what the tension is in each of those pieces of rope. Okay? So now how would you draw a free body diagram on this? Because there's 3 different masses. Well, a lot of them would look the exact same. They all have the force of gravity going down. They have the normal force pointing up. They're going to have a tension on them, which is going out. And then we don't have any friction. So they're all actually going to look the same. But there's 3 masses. Well, when dealing with tension, when dealing like this with multiple masses, it's best just to keep things simple. Okay, if I want to know how much, let's start with T3, being it's the one right behind the force there. If I want to find how much tension is in T3, we just have to remember that tension, we don't have an equation for it, but it's just another form of force. Okay, so tension can just be written as MA if you know enough about the problem. We could do the exact same with T2. We could write T2 as MA. We could write T1 as MA. We just need to know what these things are, right? So you have to look at the tension as what is causing the tension. Okay, so that's how we're going to deal with these problems. What is causing the tension? Why is there T1? Why is there tension in T1? Well, T1 is caused, right? There's tension in the rope because it is pulling this 2 kilogram mass. If the 2 kilogram mass was not there, there'd be no tension in T1 because it's not pulling anything. It wouldn't be taut. There's no tightness in the rope or anything. So the cause of T1 is this 2 kilogram mass. That's what we're going to use down here. Okay, I'm going to put 2 for that. How about T2? What is causing the tension in T2? You might want to say, well, it's the 5 kilogram mass. That's what's connected. But even if the 5 kilogram mass wasn't there, you would also have this 2 kilogram mass getting pulled. Okay, so what is happening on T2? What is causing all that tension on T2? It has to pull 5 kilograms, and in effect, it also has to pull another 2 kilograms. So T2 is responsible for pulling 7 kilograms worth of mass. Hopefully you see where I'm going with this. For T3, all the way there at the very front, that has to pull everything, right? That pulling 10 kilograms, it's pulling 5 kilograms, it's pulling the 2 kilograms, it's connected to the entire chain, the whole chain has to move. So this gets 17. Okay, so we're close to solving out our problems here. I just need to know what the acceleration is. Well, all right, so to figure the acceleration, we have to look at how much is being pulled and by what force, right? So this is being pulled by 100 newtons of force. And I know that all forces are equal to ma, even the acting force, even the force that is pulling. How much mass is the acting force pulling? Well, if this is hooked to a bus or a car or a train or a person or whatever it is, they have to pull all of it, right? Because it's all connected. So they're going to have 17. Okay, they're going to have 17 kilograms for their mass. How hard are they pulling? They pull with 100 newtons. Okay, 100 newtons. What's the acceleration? Okay, so we can solve for that. We do 100 divided by 17. I should have picked some better numbers, but it's an example. And we get 5.9. 5.9 meters per second squared. Now that's the acceleration of the entire chain here, right? All 3 of these are tied together. The whole thing will move with an acceleration of 5.9, which means all 3 of these tensions are going to see an acceleration of 5.9. Okay? Which means this, 17 times the 5.9, if we left everything out, this is right around 100 newtons. Okay, you might actually get just a little bit of a different one because we did do some rounding, but it should be right around 100 newtons in that first rope, that first tension. The next one down, we do 7 times 5.9, and we get around 41. Okay, a little less tension in that secondary rope. Down on the third rope, we have 2 times 5.9, which is just 11.8. Okay. So you can see how the tension varies depending on how much they have to pull. So if you're developing some kind of a setup that has to, like maybe a train system or some kind of a conveyor belt, it's important to know how much mass is at what point on the belt, because that'll dictate how much tension each of these need to withhold. This is why we have limits for elevators or escalators. If you've gone skiing, the lift that brings you up has a specific number because the tension on it matters, the number of cargo that goes through. When you go onto a plane and your baggage is overweight, there's a reason for that. Okay, and that they can then maneuver it onto the plane to get the correct situation there so that their plane works, their lift and everything works correctly and they're balanced. Okay. Also, if you have different materials, say you had a couple of different choices for T1, T2, and T3. You would want to put your strongest choice of material, your strongest rope, up near the front, because a weak rope could be in the back, right? Because it only has to handle 11.8. Also, if you think of a train, of a whole bunch of train cars, the couplers that connect the two cars together, that first coupler that connects onto the engine has to withstand all of the weight behind it. Okay, whereas the caboose, the last one that goes on, that coupler only sees the weight of that last car. Okay, so there's just a couple of real world examples of some things like that, and how engineering takes place, based on those things and based on the forces. Okay. Okay, sounds good. On to the next one. I think we've got one more example here, and then I'll probably end it. All right, example 5. So this is a common one that comes into physics. A lot of students kind of hate this problem, but it is important to go over. It is important to know, and it's kind of a challenge. If you can do this problem, then you do understand a lot about tension and the directions and a lot of the math that we have learned in the previous chapters. So it is a good example. If you're taking homework on this one, I'm pretty sure you will have one of these in your homework, or you might expect one on an exam. But what we have is a weight that is being hung from a ceiling, right? A vertical hanging, like a chandelier. This could be a traffic light. This could be any kind of object that you can think of hanging or suspended by a pair of ropes or wires or cables. Okay. So in this one, we have 3 cables. 3 cables support this 122 Newton block. T1 and T2, those cables are only rated to withstand 100 newtons. We see the block is 122. It also says T3, this cable, can support 200 newtons. And the questions are, the question is, will the cables hold? Will they break? Is the rating high enough? So what we really need to do is find the tension in all 3 cables. I need T1, T2 to see if they're less than 100. And then I need T3 to see if it's less than 200. Okay, so we do need to know all 3 of the tensions. So if we look at the object, the 122 Newton object, let's start there, being we can draw out a free body diagram. I have that object being pulled down by the force of gravity, which is just m times g. I also have what is holding it up. So normally we would have like a normal force. Well, in this case, we don't have normal force, but we do have a rope that is pulling it up. And that rope is T3. Okay. And then from there, I have these other tensions that are also pulling on that as well. There's a point of equilibrium here where these 3 cables come together and everything there is 0, right? So I actually have T2 coming in. T1, T2. And T3 coming in. And those all balance out. Those are all in equilibrium as well. So I really had to kind of break this into 2 different parts, right? So I'm going to look at one with the mass that's hanging, and I'm going to look at one with just the chains. Okay, first I need to figure out what T3 is. And this is the easiest one to figure out what T3 is, because T3 is in both of these problems. So for T3, if it's in equilibrium, this is only in the y direction. There's nothing in the x. So for T3, we have T3 pointing up, and we have FG pointing down. Now, I know that it's in equilibrium, which means this can be written as a 0, which means that T3 is just equal to Fg, okay, the force of gravity. Now, it didn't give me a mass. I know that G is 9.8, but in fact, I don't actually need that because it told me it has a weight of 122 newtons, which is Fg. So this is 122 newtons, which means that T3 is going to equal 122 newtons as well. Let's see, I guess I kind of got a bit together there. Yeah, it's a little better. All right, so T3 is the easy one. T3 will withstand 122 newtons. It has to support the entire block. So maybe intuition could have told you that T3 supports the entire block, especially since the last example. So T3 is 122 newtons. So yes, T3 will hold. Okay, so that part is good. That part is done. We can add that over here if we would like. We should see what T1 is. We should see what T2 is. And T3 is 122 newtons. Check. Okay. Now the other ones, we got to use this drawing. Okay. So if T3 is 122, it means that I have 122 newtons going up, and these two going down. They have to counter it because, again, we're all in equilibrium here. But these are at angles. What do we have to do when they're at angles? We have to break them down. Okay, they have to be broken down into x's and y's in order to be able to do this. Now, T3 is straight up and down. These are at different angles to each other. It wouldn't make sense to rotate because no matter where you rotate to, you're only going to be able to satisfy one of them. So we'll go ahead and we'll break both T1 and T2 down into x, y components. And then that way we'll get a very different looking picture. Like for instance, T1 goes down and to the right. So if I were to draw that in a free body diagram with it being broken down, I would have a T1y, a T1x, okay, like that. T2 would be done the same way, but that goes down and it also goes to the left, which means I will have a T2x and a T2y. Okay, and then I will have T3 coming up. Okay, so this got a little bit big here, but this is what is happening, right? So each of these are pulling in an x direction. They each have a y component, and we have a T3, which is 100% in the y. There is no x component on that, all coming up. So what I have to do to solve for these is sum up my forces. Now I know that these are all in equilibrium. That block I do not want to fall. I want it to stay the same. So just make these 0 right off the bat. All right, you can erase them and put zeros like I've been doing. You can write in zeros if you want, it doesn't matter. Let's make them zeros. In the x direction, what do I have going on? I have T1 pointing in the positive direction, so T1x minus T2x. T2 is pointing in the other direction. Those are the only two in the x direction. Okay. How about for the y direction? What do I have? Well, I have T3 pointing up. Okay. And then I have both of these pointing down. So I'm going to have a minus T1 in the y and minus a T2 in the y. Okay. Whew. We got quite a bit going on here. So I have these now. I know everything's equal to 0, so I'm going to go ahead and just take these out. If this is equal to 0, I know here that the T1x is equal to T2x. Okay, and that'll take care of that equation, right? I can rewrite it like that. T1 is equal, or T1x is equal to T2x. Now, how am I going to get the x component of T1? If it didn't tell me what T1 is what I have to solve for. So how am I going to get that going in there? Well, I can write that in a couple of different ways, right? If I just want the x component of T1, right? I just want the x component. That's up here. Right? That's this, T1x. So what would that be? Well, the T1x component would be, right, the adjacent leg of the triangle. T1 would be the hypotenuse, the whole thing of the triangle. So T1x would actually be written as T1, and then again, adjacent, so we're doing cosine. Cosine of 37. That's T1x. That's the leg of T1 that's in the x direction. Similarly with T2, we'll have T2 cosine of its angle 53. Okay. All right, did that get me anywhere? Still, I don't know T1. I don't know T2. I know these cosines are just numbers, but I can't go any further. All right, I have too many unknowns. I need T1, I need to solve for T2, and I don't have anything to plug in. That's as far as I can go with it. So what do? You have to go to the next one. Okay, you go to the next equation. Now, I've got T3y. I know T3y. T3y is 122 newtons. Okay, so I'm going to put 122 newtons for T3y. Now I'm going to add T1y to the other side, and I'm going to add T2y to the other side. And that gives me this. Now I'm going to do the same trick with these, right? I have 122, and that's equal to, what is T1y? Well, if this was the cosine, y would be the sine. So I'll have T1 sine of 37 plus T2 sine of 53. Okay? But I'm now still in the same boat. I don't know what T1 is. I don't know what T2 is. But everything else is just a number. So if I could somehow just get one of these solved, I'd be in business, right? So this is what we call a system of equations in physics, in mathematics, and in life. You have two unknowns, T1, T2, but they show up in multiple equations. They show up in one equation and another equation. So what we can do is we can actually solve for one of these and plug it into that other equation. And it's going to get a little messy in there, but we can do it, and we'll end up solving out for it. So what I mean is, I don't know what T1 is, I don't know what T2 is. I'm going to solve for T1. I'm just going to solve for one of the unknowns. And that will give me T2 cosine of 53, all divided by the cosine of 37. Okay? And these are just numbers, right? But it's giving me a relationship of T1 and T2. I'm going to take that T1, and I'm going to plug it into this equation. Okay? What is that going to do? It's going to eliminate T1, and it's going to make the entire thing in terms of T2. That will leave me with 122 is equal to T2. Let's see, I'll put this down here. T2 times the sine of 37 over the cosine of 37 times the cosine of 53. Okay, so hopefully that makes sense. Here's my T2. Here's my cosine of 53. I'm dividing by the cosine of 37. And this was, I'm subbing in for T1. T1 was originally times the sine of 37. So I've added that one in there as well. Okay. This just gives me a sine over cosine, gives me a tangent. You can know that from trig if you want. You can also just leave it as sine over cosine. It doesn't hurt anything. Now I just need to continue along and say this is equal to, this is plus. I need to finish it. I can't forget about it. Plus the sine of 53. All right, so now I've got a number equal to T2 times a number plus T2 times another number. All right. At this point, being it's algebra based, a little bit of calc based, I like to just get numbers. All right. I don't want to keep it in all these sines and cosines and whatnot. Let's go ahead and let's just get this thing down into some numbers so we can see what's going on. So I'm going to have 122 times T2, and then that's all, it's just a number. Let's do the sine of 37. I'll do it the long way, divided by the cosine of 37. and then multiply that by the cosine of 53. And if all done right, we get a 0.45. Okay? That's this into here. Now, plus T2 times whatever the sine of 53 is. Okay, you just plug that in, you get a 0.80. Okay, that looks a lot easier to solve for now, right? If I've got T2 times this plus T2 times that, I can factor out a T2 and I can add those two numbers together. This will give me a 122 is equal to T2 times 0.45 plus the 0.8. Okay, now we can solve for that. That should be some basic algebra for you. I want you to go ahead and put that in. Get used to doing these. Take 122 and divide by that number, that sum that you get. And you will get a T2, hopefully, a T2 equal to 97.6 newtons. Now, is that in the right ballpark? Well, they said they needed to withstand 100, so that is in the right area, just barely. But T2 now works. Okay, we've got a number for T2. Once you solve for T2, now you can go back and plug in what T2 is, and finally we can solve out for T1. All right, so I'm going to go over here. I'm going to go back to this equation. I made this equation equal to T1 based on T2. Okay, so I'm going to take that equation. Sorry, I have to erase. It's a whiteboard. I'm sure you want to keep that in your notes, which is fine, but I just have to kind of bounce around. It's just the way I have to go here. So T1 is equal to T2. I know what T2 is, 97.6. That's times the cosine of 53. And this whole thing gets divided by the cosine of 37. That's just a number now, okay? It's just a number we can plug in. We'll go 97.6 times the cosine of 53, and then divide this whole thing by the cosine of 37. And what do we get? Well, for that one, we get a little bit less. We get a T1 now is equal to 73.5 newtons. Okay, so that then comes over here. We can finish out our problem. 73.5 newtons. That one also passes the checklist. Okay. And we can finally now say with certainty, will the cables hold as a yes or no question? Yes, the cables will hold because each of their tensions, 1 and 2 are less than 100. T3 is less than 200. All three of these will work. Okay, so that is a lot of trig. It's a lot of breaking things down and keeping things in order. Also, there's the first look at systems of equations, adding things in. Good thing to get in the habit of. It's a common algebra thing where you have x's and y's. You've probably seen them numerous times as having x's and y's, and you plug in an x and a y into an equation back in algebra. Same thing here, except for that it's instead of x and y's, I'm calling them T1 and T2. Okay, but same principles. Okay, hopefully that made sense. Hopefully this chapter is going okay for you. This is a long chapter, a tough chapter. Lots of examples, lots of things you can do.